Hello friends, in this video we will see how to calculate position and velocity of a particle using integration, and this we will discuss for a particle that is moving in a straight line. This means motion in one dimension. Now discussion of this topic requires little bit knowledge of integral calculus. So I assume that you have some idea of differentiation and integration. Now in the previous videos we have seen how to calculate position, velocity, these terms for a case when the acceleration is constant. Basically, if you have a one-dimensional motion and acceleration is constant, you can apply three kinematical equations to calculate distance and velocity at any given point of time or at any given distance. What was that formula? So if you remember, those formula was, one formula was S is equals to ut plus half at square. So this is one formula, and in this case remember acceleration is constant. That is the most important point. In this case acceleration is basically constant. That is the important point we have. Another kinematical formula that we have, that is v square is equals to u square plus 2as, where u is the initial velocity, a is the acceleration, v is the final velocity, and s is the displacement traveled. We can also calculate v using third formula, that is v is equals to u plus at. Now we can use these three formula to calculate distance and velocity only if acceleration is constant. Now the question comes, what if acceleration is not constant? How we deal with that situation? How we calculate position or how we calculate velocity of the particle at given point of time or at given distance? How we do that? So in this case I can say if acceleration is not constant, in that case I cannot apply this formula. So when acceleration is not constant, the equation that we derived in that section is no longer valid. So this equation that we derived earlier in the previous video is no longer valid because these derivations assume that acceleration is constant. So now I cannot apply these equations because acceleration is not constant. Then what should we do? In that case we have to go from the definition of instantaneous velocity and instantaneous acceleration. If you remember, we have derived or we have defined average velocity, that is delta v is equals to delta x divided by delta t. So this was the average velocity expression. Now in the limiting case, when delta t tends to 0, this average velocity becomes instantaneous velocity. So in the limiting case I can say when delta t tends to 0, this average velocity becomes instantaneous velocity Vx, and this becomes delta x by delta t, this becomes simply dx by dt. So this is the expression for instantaneous velocity. So now when the acceleration is not constant, we will try to work with the instantaneous velocity expression, that is Vx is equals to dx by dt. Similarly, we will work with the instantaneous acceleration expression. Instantaneous acceleration will be Ax is equals to dvx by dt. So this is same expression. Similarly, you can calculate average acceleration similar to average velocity. You can calculate average acceleration. So this is average acceleration, and this is equals to change in velocity divided by change in time. And if you take limiting time, that is delta t tends to 0, then this average becomes instantaneous. So in that case you will have average velocity, this will become your instantaneous velocity, and this becomes simply dv by dt. So now we have these two expressions. For first expression, this is for one dimensional motion, that is Vx is equals to dx by dt, and the second expression, that is acceleration ax is equals to dvx by dt. So now if I know acceleration, then how we calculate velocity? So the first point is, in many situations or in many cases, acceleration as a function of time is known. So in many cases, acceleration is known as a function of time, but not the velocity and the displacement. So if I know acceleration, so in this expression acceleration is known, then what is my target? And acceleration is known as a function of time. Then from here, how we calculate velocity as a function of time and how we calculate displacement as a function of time. So this is the challenge, how we do that. So my acceleration is known and this is known as a function of time, and I want to calculate velocity and position vector as a function of time. So the question is, how can we find position and velocity in a straight line motion from acceleration function, that is at? So I know acceleration function, that is at. It can be any kind of function. For example, it can be a linear function a plus bt, or it can be quadratic function. Depending upon the problem, it can have a different kind of function. So if I know this function, how we calculate velocity as a function of time and how we calculate displacement as a function of time. So this is the idea that we have to solve. This is the problem that we have to solve. To solve this problem, basically there are two approaches. The first approach is graphical approach. So let us say acceleration as a function of time is known to me. So I know acceleration as a function of time. So this is the graph of acceleration as a function of time. So this graph is known to me. Now what is my target? My target is to calculate velocity as a function of time. Now in this graph, on the x-axis we have time, on the y-axis we have acceleration, and this is one-dimensional motion, so we have ax. So now let us consider, if you remember, we have this formula, that is average acceleration is equals to, so this is average acceleration. So average acceleration in the x direction, if I consider, this is equals to change in velocity in the x direction divided by delta t. I can also write this expression, that a change in velocity in the x direction is equals to average acceleration in the x direction multiplied by delta t. So this is the expression, same expression written in a different manner. Now this expression gives me a hint. What is the hint? That is, if I want to calculate change in velocity, then I can multiply average acceleration and delta t. So what I will do is, idea is we have to find some small value of t, that is delta t. So using this idea, let us divide this time interval from t1 to t2 into a small intervals. So what we have? So this is my acceleration time graph. So this is the acceleration time graph, and this graph is given to you from time t1 to time t2. So basically you know what is the instantaneous acceleration at time t1 and what is the instantaneous acceleration at time t2. Now what we are doing is, we are dividing this time interval from t1 to t2 into different parts. One part is this, one part is this, another part is this. So we are basically dividing time a scale into a small parts. And let's say any small part is called delta t. So this small length of this small time interval is delta t. Then what we will do is, we will make one rectangle. So this is the rectangle that we have. Now for this rectangle, if you see, for this rectangle, the acceleration is not constant. For example, acceleration is varying from here to here. So for this point, this is the acceleration, this point, this is the acceleration. But if you consider delta t is very small, I can assume this acceleration is constant. Or what we can do is we can use average acceleration. So let's say I can say for this time delta t, the acceleration is the middle value or the average value. So this corresponds to the average acceleration. So this means for this rectangle I know average acceleration. So if I know average acceleration, I can multiply by dt and I can get change in the velocity in the x direction, and that is written here. So if I want to calculate change in the velocity, what we have to do is we have to take average acceleration for that small interval and then I have to multiply by delta t. Now what this term graphically means, so this is average acceleration multiplied by delta t. This term is nothing but area of this rectangle. So this is average acceleration is this much, so this is the height, and delta t is the width. So height multiplied by the width, that is nothing but the area of this rectangle. So this term, that is a average in the x direction multiplied by delta t, this term is nothing but area of this small rectangle. So I know what is the change between this time interval delta t, that we can calculate simply by calculating the area of the small rectangle. Now if I want to calculate what is the change in velocity from time t1 to time t2, how we will do that? Idea is again same. What we will do is we will calculate all this area. So this area plus this area plus this area and finally plus this area. So if you calculate all these rectangular areas and then sum, then you can calculate change in velocity between time t1 and time t2. So we can write change in velocity in the x direction from time t1 to time t2. This is nothing but sum of all the areas, that is average velocity in the x direction. So average velocity in the x direction multiplied by dt, and this is from time t1 to time t2. So simply if you add all this area, then you can find what is the change in interval or change in the velocity from time t1 to time t2. So the total x velocity change is represented graphically by the total area under the curve between vertical lines t1 and t2. So if I want to calculate what is the change, in that case basically we have to calculate the area. So what is the change between v1 to t1 to t2? So let's say at point t1 velocity is v1 and at time t2 velocity is, let's say, v2, and this is approximated. So this velocity is v2. So this is v1 and this is v2. Now if I want to calculate what is the change, so this means what is v2 minus v1, that is nothing but change in velocity in the x direction, and this is nothing but total area between time t1 and t2. So this is equals to total area between t1 and t2. So if I can calculate this area, I can calculate change in the velocity. So this is the graphical approach. In graphical approach, what is the idea? You basically divide the time axis into a small regions, and once you have a small regions, for each a small rectangle you calculate the change in the velocity and then you sum up, and if you sum all these rectangles area, you get what is the difference in the velocity or what is the change in the velocity between time interval t1 and t2. We can also calculate change in velocity using analytical approach, and this is basically extension of the previous case. So in the graphical method I said, if you want to calculate change in the velocity in the x direction, then this is equals to average acceleration in the x direction multiplied by time interval delta t. Now if you want to calculate this change between time t1 to time t2, then you have to basically sum. That is, you have to consider summation of all the rectangular areas. Now the question is, what will happen if my delta t, that is time interval, goes to 0? Very small time interval. Physically this means if the time interval is very small, my rectangle will be very small. So area in that case I can calculate using integration. Basically first, if delta t tends to 0, this average acceleration in the x direction will become instantaneous acceleration. So if delta t goes to 0, basically in that case average acceleration in the x direction, this tends to instantaneous acceleration in the x direction. So now in that case basically I can calculate this change in velocity in the x direction using integration. So if we have discrete summation, so this is what? This is discrete summation. So you are summing one rectangle, second rectangle, third rectangle. So this is a discrete summation. But when you have delta t tends to 0, the discrete summation becomes integration. So this is the idea. So in that case, we can calculate change in velocity in the x direction simply using integration. So this is the sign of integration. And this average velocity or average acceleration in the x direction becomes instantaneous acceleration in the x direction. And the time delta t, since this is very small, this becomes dt. So I have to integrate ax with respect to t, and I have to integrate between time t1 to time t2. So that will give me change in velocity from time t1 to t2. So that is what here we have. When delta is very small, then the area under the curve can be calculated using the integral. So what we were doing that time? We were basically calculating the area under the curve. That was the rectangular area. So if you sum all these rectangular areas, that was the area under curve. Now if delta t is very small, then this discrete summation can be exchanged with the integration, and that's what we have here. That is ax dt, and I am to integrate between time t1 and t2. That will give me the change in velocity in time t1 and t2. So if my time t1, velocity at time t1 is v1 and velocity at time t2 is v2, then change in velocity I can write simply nothing but v2 minus v1. So this is v2 minus v1 is equals to integral t1 to t2 ax dt. So from here I can write v2 is equals to v1 plus integral ax dt time t1 to time t2. One special case, when time t1 is 0, then I can write simply v2 is equals to v1 plus 0 to t, let's say time t2 is t, then 0 to t ax dt. Basically ax is a function of time. So this expression I can use to calculate velocity at any time t2, where t1 is 0 and t2 is t, and velocity at time t2 is v2 and velocity at time 0, that is v1. So I can use this expression. This expression involves instantaneous acceleration. So I have to integrate the instantaneous acceleration, that will give me the change in the velocity, and I have to add the initial velocity to get the final velocity of the particle. So this was the procedure that we can follow to calculate the velocity. If the instantaneous acceleration is given, instantaneous acceleration as a function of time is given, then I can integrate and I can get the velocity. Now the next question comes, what we do or how we calculate displacement. We know now velocity as a function of time, and I have to calculate acceleration, displacement as a function of time. So we can use the same idea. That is, if I want to use graphical approach, we have to make a diagram. In this case, this axis will be velocity. So y axis is my velocity and x axis is the time. And then we have to basically take a small rectangle, and time will be delta t, very similar to the previous case. And then we have to use the concept of average velocity. So if you remember, we defined average velocity in the x direction. This is equals to change in displacement divided by change in time. So from here I can say delta x is equals to average velocity in the x direction, this multiplied by delta t. This is what? If I consider this point, so this is, so for this rectangle, so let us consider this rectangle. For this rectangular, this is the average velocity. So let us see, this is my average velocity in the x direction. And this is time, delta t, time interval. So if I multiply these two terms, I will get this area. That is area of this rectangle. So area of this rectangle, that is velocity and time graph. So this is velocity versus time graph. So area of this rectangle is nothing but average velocity multiplied by delta t. That will give me the change in displacement delta x between time interval delta t. And if I sum all this from time t1 to t2, that is, if I take all this area, if I sum all these rectangular areas, then I will get change in displacement between time t1 and t2. Now, in a special case, as I said earlier, if delta t tends to 0, what will happen? If my delta t tends to 0, these rectangular will be very small. So these rectangles will be very small. So this rectangle, something like this. So this will become very small, very fine rectangle. So in that case, I can replace delta t with dt. What about average velocity in the x direction? I can replace this with instantaneous velocity in the x direction. So that is when we have delta t tends to 0. And also we can replace continuous or basically discrete summation with integration. So that is what the three changes we are going to do if delta t tends to 0. So in this way, basically now if I do all this modification, I can write delta x is equals to, since this summation becomes integration and this average velocity becomes instantaneous velocity and this delta t becomes dt. And I have to integrate from time t1 to time t2. So this will give me the change in position vector, that is change in displacement between time t1 to t2. So let's say at time t1 the object position is x1 and at time t2 the object position is x2. So if I plug this, delta x will become change in position, that is x2 minus x1, and this is equals to t1 to t2 vx dt. So from here I can write x2 is equals to x1 plus integral t1 to t2 vx dt. In a special case, if time t1 is 0, then I can basically write the same expression little bit modified form. So I can write x2 is equals to x1 plus 0 to time t2 is t1. Time t2 is t. Let's say time t2 is t. Then I can write x2 is equals to x1 plus 0 to t vx dt. So I can use this integration to calculate position of the particle at any point of time t, and that is given by x2. So in this video we have seen how we can calculate velocity and position of the particle if acceleration vector is given, that is a function of time. So there are two approaches. One approach is graphical approach, another is analytical approach. We will use analytical approach in the coming videos. So in case of analytical approach, what we do is we use advantage of integration. So when you have discrete summation in case of delta t tending to 0, it becomes a continuous summation. So we use this fact and then we can calculate velocity and position as a function of time. And I hope you enjoyed this video, and if you enjoy, please share with your friends, and I will see you in the next video. For the time being, bye, take care.